Hello, ladies and gentlemen. What we will be discussing in this video today is going to be some properties about logarithms. Two particular things we're going to be addressing are how do you evaluate a logarithm, meaning if I say the log of 10, what does that equal? What does that actually produce as a number? That's what we're going to do as far as how we're going to evaluate them. And the other thing that we're going to do is talk about how we graph logarithms. Now what you're seeing here, where it says f of x is equal to the log with base b of x, this is, oops, let me get my pen going here. This is generally what we would consider to be the parent function of a logarithm, where this lowercase b is a subtext here. This is going to be the base of our function, just like it would be the base of an exponent. A logarithm must have a base. Now, here it's saying that b has to be greater than 0, and that has to do with the fact of the domain of the function, and I'll explain a little bit more about that in a little bit, and also that the base cannot be equal to 1, and the only reason that the base cannot be equal to 1 is really because in an exponent the base can't be 1, and since logarithms and exponents are inverses of each other, if the base can't be 1 in an exponent, it can't be a base in a logarithm either. And here what we're seeing, where it says f of x is equal to a times the log base b of x minus h plus k, these again are simply the basic transformations that we follow for any function, where the a term would represent, that's where I would kind of be multiplying with something that causes a vertical stretch or compression. It would also cause me to reflect over the x-axis if it was a negative number. The stuff in the parentheses affects horizontal transformations, and the k at the end affects a vertical transformation, and they follow the exact same properties of every single other function that we see. So, why are you not turning? There we go. I don't know. It's having issues today. Now, what we're seeing here about properties of a function, or properties of a logarithm, I should say, the domain of the function is going to be everything that is greater than 0 to a positive infinity. And let's go back a little bit about exponents. In an exponent, the domain was all real numbers. However, the range of exponents was from 0 to positive infinity for an untransformed, basic exponent. Well, since exponents and logarithms are inverses of each other, what that means from a domain and range standpoint is that the domain of one function is the range of its inverse. So since the domain of an exponential function was all real numbers, then that means that the range of a logarithm must be all real numbers. And since the range of the exponential functions was from 0 to infinity, then that causes the domain of a logarithm, its inverse, to have a domain of 0 to infinity. So that's one of the properties about about inverses in general, is that the outputs of one function are the inputs of its inverse. So that's why the domain of a logarithmic function has to be anything greater than 0 to a positive infinity. Obviously, we can do transformations that will change particular domains of functions, but in general, that is going to be what we think of as the domain and the range. So there is no, since the x values cannot go to 0, that means that there is going to be no y-intercepts. So in a basic logarithmic function, it will never touch the y-axis because that will produce a vertical asymptote where x is equal to 0. So if we're undefined there, if we're undefined when x is 0, we can't actually touch the y-axis. And that's where x has to equal 0. Now these 3 points right here, these are super important. These are going to be the things that we will be looking at when it comes to graphing a logarithmic function. And if you notice, they have a striking resemblance to the three key points from our exponential functions as well. In fact, they follow the same inverse property. In an exponential function, the three key points that we used were 0, 1, 1 and the base, and -1 and the reciprocal of the base. Well, as I was explaining a second ago about the domain and range, the fact that the functions are inverses of each other, exponents and logarithms that is, the output of one function becomes the input of the other function. So it makes sense that since they're inverses of each other, the three key points that we're going to look at for logarithms are essentially the same three key points that we look at for exponents. However, they're going to be in the opposite order. So instead of saying 0, 1 for an exponent, I say 1, 0 for a logarithm. And instead of saying 1b for 1 in the base for the exponent, I say the base and 1, and so on. And so these are going to be the three key points. Now, if you can remember one or the other, if you can remember the three key points for a basic exponential function or the three key points for a basic logarithmic function, then you should be able to do either one, as long as you, again, kind of recall that the outputs of one function become the inputs of the other function when they're inverses, and that's what exponents and logarithms are. So the last couple of key points here are just some basic attributes of a function when we graph it. If the base is going to be greater than 1, then it will increase over time. And if the function has a base that is between 0 and 1, meaning like it's a fraction like 1/2 or 2/3, something like that, then it will be decreasing over time. And this is going to apparently be an issue. I don't know, maybe I need to just restart my computer. But anyway, we'll finish this out. Here, what we're talking about here, I just want to show you that just like with exponents, we can use pretty much any number that we really wanted to as a base of a logarithm. Okay, but there are two particular bases that get used the most. And what you're going to see is what we would refer to as the common log and the natural log. Common log has a base of 10. And it has a base of 10 because that is what our number system is based on. Our number system is based on the number 10. And as a result, we refer to that as the common log because, well, that's what our number system is based on. Sorry to seem to be repeating myself. But the second most commonly used logarithm, the number that we commonly use as a base, is actually the number e. Now, we refer to that as a natural log. Now, I don't know why we don't say NL instead of LN for natural log, but they didn't, ask me my opinion when they decided to make this stuff up, hundreds of years ago. So we just refer to LN as the natural log. Now, LN is the same thing as saying log to the base e of x. So if you see it as log base e of x, or if you see it as the natural log of x, recognize it as the same thing. And going back to the common log, because it's the common log, anytime that you see a log written without a specific base written there, you need to recognize that it is understood that it's implied that the base must be 10 if there is no specific base written. Okay, and depending on the type of calculator that you use, we have one button that says just log, and we have another button that says LN for natural log. And those buttons are programmed on every calculator that you see to only do math, to only do those operations in a base 10 or a base E. Okay, anything else that we want to do, we'll have to figure something else out to do some operations with bases that are not base 10 or base E, but we'll show you that in later videos. Okay. So here, this is the first thing that I told you guys that we were going to be evaluating, is how can I tell what does the log of something actually produce as a number? Now, in previous videos, what we did is I showed you how to convert a logarithm into an exponent and an exponent into a logarithm. Now, I know we're saying to evaluate what is this number, But in order to evaluate it, what I'm really going to do is I'm going to treat it like it's an equation, where I'm going to say the log of whatever I'm looking for is equal to x. And in order to do, the whole reason I'm doing that is so that way I can convert it from a logarithm into an exponent. So I'm going to say 6 to the x power must be equal to 216. Now, those of you with a calculator can just start plugging in and say, okay, well, what is, 6 to the what power? What is it equal to? Or what power do I have to raise 6 by to make it equal to 216? Okay, well, if you don't happen to have a calculator, we'll do our division method, and we'll say, okay, well, 6 goes into 216 36 times, 6 goes into 36 6 times, and 6 goes into itself 1 time. So there's my remainder. So that tells me that 6 to the third power is equal to 216. So here I would say 6 to the x power is equivalent or equal to 6 to the third power. So in this case, x would have to equal to 3. So that is essentially what we're going to be doing when it says to evaluate it and say, okay, well, what does this produce? Okay. Same thing here on the log base 5 of 1 over 25. We'll just kind of turn it into an equation here by saying that is equal to x. Use the little, circle thing here that we're talking about as far as how we convert it. So I'm going to say 5 to the x power is equal to 1 over 25. And so here, again, I'm going to look at it and say, okay, well, what is 1 over 25? We can say, well, 5 to the x power would be the same thing as 25 to the negative first power, and find a common base again. And so 25 to the first, how I would change 25 is I would say 5 squared, and it's multiplied to the negative 1 there. So that is going to tell me that x would be equal to negative 2. And so this is how we're going to be evaluating a logarithm by saying, okay, well, what would that kind of simplify to be? And in this case, we would say log of 216 is going to be equal to really 3, and log base 5 of 1/25 is really going to be equal to a negative 2. Ugh, this is going to get old fast having to do that, but okay. Last two examples. These are, again, I wanted to include these here because these are the most common. E is one of the most common bases that you're going to see when it comes to logarithms. So this one could very easily have been written as ln to the cube root of e. Okay, so I just want you to understand that that could be written either way. So let's just go ahead and take it for what it was given to us, and we'll say log base e of the cube root of e, and we'll just say that's equal to x. And we're going to kind of do this the same way that we have been doing it. So I'm going to say the base raised to that power is equal to this. So I'm going to say e to the x power is equal to the cubed root of 3. Okay, and again, I don't know what, I apologize, I don't know what I'm doing. I'm seeing 3's everywhere. So this is not a base, or this is not a radicand of 3, it's a radicand of e. So sorry about that. Okay, now, back on the same page. What we're trying to do is, again, we want to see, can we get a common base? Well, obviously the common base is going to be e, so how do I get that e out from underneath the radicand? Well, that means I have to cube both sides. So that way this cube and the radical 3 will cancel each other out, which will leave me just e on the other side. And rules of exponents say the x in the exponent position and the 3 in the exponent position, those get multiplied together, so I get e to the 3x power. So this, even though it's not expressly written, has an exponent of 1, so that means now that the bases are the same, we can set the exponents equal to each other and solve for x. So if we typed this into our calculator, if we said log base e, or actually on the calculator we'd have to say natural log. If we said natural log of the cubed root of e, the calculator would produce an answer of 1/3. And same thing here, I just want to show you that a lot of times you will be simply given a function that says the natural log of something, and you have to recognize that the natural log is the same thing as saying log base e. So we'll kind of do the same thing. We'll say the natural log of 1 over e to the 5th power is equal to x. So we will kind of convert this into an exponent, so that way we can try and evaluate it. So that will give me e to the x power is equal to 1 over e to the 5th. So we have the common base obviously is going to be e, so we want to, on the right side, change it from being in the denominator to being in the numerator. So I take the reciprocal of it, and in so doing, the exponent changes signs from positive to negative. Now I have bases that are the common, and so I can set the exponents equal to each other and say x in this case would be equal to 5. So again, on your calculator, if you said natural log of 1 divided by e to the 5th power, the calculator would produce an answer that says that would be -5. So that is how we're going to be evaluating functions. We'll simply kind of take the function that we have, convert it from a logarithm to an exponent, and solve it as an exponential equation so that we can see what would it actually be equivalent to. So the last thing we're going to be talking about in this lesson is how do we graph a logarithmic function. Now they follow along with basically everything else that we have been doing as far as how we identify key points. The same kinds of transformations for every other function apply to these. So here we have a function that says h of x is equal to log base 4 of x. Now this is a basic untransformed function. And in order to identify how would I graph that type of function, I'm going to use these 3 key points. So the base in this case is 4, so anywhere I have a b in my 3 key points that we see here, I'm going to put that number 4. So if I want to graph this function, I'm going to use the key points 1, 0, 4, and 1, and 1/4, and -1. Now every basic untransformed logarithmic function was going to have a vertical asymptote at x is equal to 0, which is essentially the y-axis here. So everything we are going to graph should be to the right side of that vertical asymptote. So at 1, 0, at 4 and 1, and at about 1/4 and -1. So I'm really kind of approximating right there. And we're going to follow the vertical asymptote up, go through those points, and that is essentially what the logarithmic function would look like. So from here, once we know how to identify a basic function, now let's see, can we do some transformations? Now I'm going to approach this the exact same way that I showed you how to approach a exponential function. So I want to start by looking at what is the basic function that we have here. Well, the basic function in this case would be f of x is equal to log base 3 of x, which my 3 key points, oops, I'm doing it backwards. My 3 key points of any logarithmic function are 1, 0, the base and 1, and the reciprocal of the base and -1. So the 3 basic points, or the 3 key points for the basic function, I should say, are going to be 1, 0, 3, 1, and 1/3, and -1. So I'm going to go ahead and kind of mark where those are going to be. So 1, 0, 3, 1, and about 1/3 and -1. So, and it would have a vertical asymptote at y is equal to 0. Now let's look at the transformations. So So the x plus 1 in parentheses, that says to shift the function left 1 unit, so that's a side-to-side motion. So mathematically, that would simply say to subtract the x numbers by 1. And the other transformation that we have is a plus 2, and that is going to simply say to shift the function up 2 spaces. And mathematically, the way we would describe that, because that's going to be a vertical movement as affecting my y numbers, that's going to basically say add 2 to my y numbers. So let's apply those transformations and see what my points are going to be. Clean that up. So if I look at the transformations themselves, I'm going to subtract all the x numbers by 1. Okay, so 1 minus 0 is 0. 3 minus 1 is 2. And 1/3 minus 1 is going to be negative 2/3. And I'm going to add all my y numbers with 2. So starting again with the first point, 0 plus 2 will give me a 2 here. 1 plus 2 gives me a 3 here. And negative 1 plus 2 gives me a positive 1 here. So those are going to be the 3 points that we should end up at. Now I'm going to kind of take a look at how I would look at it just visually with the graph as a transformation. I'm going to start here at 1, 0, and I'm going to do the transformations that we've identified. I'm going to go to the left 1 space and up 2 spaces, and I should have a point right there. And here, if I go to the left 1 space and up 2 spaces, I should be right here. And again, to the left 1 space and up 2 spaces, we should be right there. And again, if we shift the entire function to the left 1 space, my vertical asymptote will also shift. So here is the graph of the transformed function. Either way that you want to do it, simply plot the basic points and then do the transformations, or do the transformations to the actual coordinates and then plot those points. Now again, as you're going through these, if you have any questions, make sure you're writing them down and bring them to me in class. So here what we're going to be looking at is essentially, this is going to be our last function that we're going to be graphing. And I specifically wanted to look at one that was a natural log, because this is going to be a very common thing that we're going to be looking at, where we have to start getting more familiar with using e as the base, or e as a number. So the basic function in this case, again, every logarithmic function follows these points, 1, 0, the base, and 1, and the reciprocal of the base, and negative 1. Okay, so the basic points in this function would be, since the base is e, let me go ahead and write that out. The basic function, oops, I can't spell. The basic function with no transformations would simply be f of x is equal to the natural log of x, or if you need to write it this way so you can see the base more clearly, log base e of x. So the points that I'm going to use for the basic function will be 1, 0, and 2.7 for e, and about 0.4 for the reciprocal of e, just like what we had with the exponential functions. And so I'm going to go ahead and identify where those points are. So 1, 0 again, and about 2.7 and 1, so about right here, and about 0.4 and negative 1, so probably could move that one a little bit over. So I'm going to go ahead and do that because it is a little closer to the halfway mark. Okay, and of course the vertical asymptote of the basic function would be right here. So now what we're going to do is see what transformations are happening. So the negative sign, so we'll just say negative natural log, so that negative is really what we're looking at. Because it's essentially saying -1 times the function. So there's no vertical stretching because we're only using 1, but the negative itself says to reflect across the x-axis, which would essentially mathematically would tell you multiply the, so that's an up and down movement, multiply the y numbers by -1, and then the -2 says to shift down 2 spaces, which would, again, vertical movement is affects the y numbers. So we would say subtract the y numbers by 2. So we're going to kind of do this the same way that we would do our order of operations. I'll do the multiplication first and then the subtraction second. So let's go ahead and get our points, and then we'll plot them and see how they looked out or how they worked out with the transformations on the graph. So we're not affecting any horizontal movements at all. So the x numbers aren't changing one bit. Okay, so 2.7 and 0.4 are still the x coordinates. So I'm going to multiply all of the y coordinates by -1 and then subtract that number by 2. So 0 times -1 is 0. And subtract that by 2 and I get a -2. 1 times -1 is -1. Subtract 2 and I get -3. And -1 times -1 will give me a +1. +1 subtract 2 gives me a -1 here. So my transformed coordinates will be at 1 and -2, 2.7 and -3, and 0.4 and -1. So we're still kind of about right there. So the function itself, instead of increasing now, is going to look like a decreasing function. And there we go. So that's essentially going to be the two skills that we're looking at for the exponents, or I'm sorry, the logarithms that we're talking about here, how you evaluate them, kind of make it an equal sign or make it an equation by saying the logarithm is equal to x, and then convert it into an exponent so that way you can solve for your variable, and identifying your 3 key points of a logarithmic function so that way you can transform it in any way that you need to, and then graph it from there. So again, any questions that you had, please make sure you have them written down, bring them to me in class, and I'll be happy to work them out with you. And again, we'll see you guys in class soon, and thanks for watching.